All right, I am here and ready to help you review for the Chemistry Regent. So hopefully you can see me and hear me. The chemistry exam is tomorrow morning, bright and early. So hopefully you are ready. I can answer your questions, but I also do have up here the reference table, so I can talk about some of that. And I have the June exam up here in case you had specific questions about that exam in particular. So if you have specific questions, absolutely let me know and I will try to answer them. So you can type those in chat if you do have questions. Again, this was the June exam, and I'm going to kind of go through some of the content, hoping to call attention to some things that are repeated on many exams, but also where there were some difficulties on this exam. Okay, so for example, this first question, pretty popular question, phrase that describes the nucleus of an atom. And inside the nucleus, we have two particles, protons and neutrons. Protons with positive charge, neutrons with no charge. So that means the nucleus would always be positive. So it's this. How positive? Well, let's look at the reference table. Okay. So on the reference table, let's go to the periodic table. And however many protons an element has, that indicates what the charge of its nucleus would be. So for example, magnesium has an atomic number of 12, so it has 12 protons. So the charge of a magnesium nucleus is positive 12, okay? And then we have carbon, atomic number of 6. So that means the charge of a carbon nucleus is always positive 6. Okay. And again, that question is going to be asked in some way, shape, or form. Okay. All right. Pause for a second. I'm just going to close the door. My cat is being annoying. Okay, sorry about that. Okay, so I see your question. Is proton mass equals neutron mass? Yes, absolutely. So proton and neutron, which that is on the reference table, and that's going to be in table O, so you can always double check it. But here is proton and neutron. The top number represents mass. So you can see for neutron and proton, they both have a mass of 1. Okay, and then the charge is different. But yes, the proton number, so we said carbon had 6 protons, right? So a carbon atom also has 6 electrons because it has to be neutral. Okay. And I will, well, to answer your question, I'll go for at least an hour. If we have questions, if there's, can go for sure longer, but I'll definitely stay for at least an hour and try to go through as much as I can and answer whatever specific questions you have. Okay. Let's see. So if we go back to this exam, again, if you have a question outside of this, feel free to ask. Hello, hi. Thanks for joining here and reviewing with us for the exam tomorrow. Let's see. Wave mechanical model. So they're going to probably ask a question about the wave mechanical model. So what you should know is that electrons are in orbitals outside the nucleus. Here's the annoying thing is it can be called wave mechanical model, but also modern model, but also quantum model, but also electron cloud model. So in general, if they name the specific model, they mean the one where we have electrons in orbitals. Okay. Okay, so this one right here where it talks about ground state and excited state. I definitely want to talk about this because this is asked in some way, shape or form. I know, you know what? I see that one got you because wave mechanical, they literally call it so many different things. So just to reiterate that, wave mechanical, okay, is the same as quantum model, is the same as modern model, is the same as electron cloud model. Okay, so all of those literally are the same exact thing. It's kind of obnoxious because why would they do that? Why can't they just be consistent? So you can see them hopefully right here. Those 4 all mean the same thing. Okay, if they're talking about a different model, they won't really name it like that. Okay, they won't call it the plum pudding model. They will talk about after the cathode ray experiment or after the gold foil experiment. Okay. Yes, absolutely. So to answer, whenever they give a weird model name, yes, one of these 4 is usually what they're going to say, but yes, they mean the electrons are in orbitals. Yep. Oh, thank you. I am so glad. First, I'm happy to hear that you passed already. That's awesome. And I'm glad that my reviews helped. So that's great to hear. So for question 4, yes. So I'm going to go through this ground state and excited state because this definitely gets confusing. And I don't know which way they will ask the question. So I'm going to look at the reference table for a minute. And I'm going to go to the periodic table though. Okay. And I'm going to use, let's see, I'll use calcium as an example. Okay. So this electron configuration, right? You can see right here, it's electron configuration. Okay. This, which is listed on the periodic table, is ground state. Okay. If you can find it on the periodic table, it is ground state, 100%. So it doesn't even matter what element it is. It will always be ground state if it's listed on the periodic table. Okay. And that means every electron is in the lowest energy level possible. Okay. So what that means is you can see the first number here is 2. So that means calcium has 2 electrons in energy level number 1. It has 8 electrons in energy level 2, 8 electrons in energy level 3, and 2 electrons in energy level 4. Those are the valence electrons. And the higher the energy level, the more energy the electron has. Yes, so the valence electrons, they have the most energy. Whatever the last number is, the valence electrons, they have, yes, so to answer, they have the most energy. So yes, if I were going to write this as an excited state, here are the important things. One, I cannot change the number of electrons. So calcium, I know has 20 electrons because it says 20 right here, but I could also add these up. 2 and 8 is 10, 2 and 8 is 10, and that's 20, right? So when I make an excited state, I still have to have 20 electrons, but I need to take an electron and move it higher. So I'm going to do one example. This is usually how I tell people to do it as the easiest way to do it. So you keep everything, you could keep whatever you want. So I'm just going to 2, 8, 8. I'm going to take one of those away. And nope, you're not too late at all. Okay. And this right here would be an example of an excited state. That is not the only answer. So I'm going to give you another example of what the excited state could be. Okay. Why is this one an excited state? Because it still has 20 electrons, if I count them up. Okay. And it does not match what's on the periodic table. So an electron has to go higher. Okay. So I took one from the last one, but I don't have to do that. I could do this. I could take one from the first one and move it up like this. Okay. That is also an excited state for calcium. How do I know it's calcium? It has 20 electrons still, but it doesn't match what's on the periodic table. Okay, so it's excited state. I could even do this, 2, 8, 7, 3. That's still excited state because that one electron is up higher than it is supposed to be. Okay, so I know what element it is because I know how many electrons it has. I can just add up those numbers. And then I know it's excited state because it doesn't match the periodic table. Okay, so when an electron is in ground state and moves up to excited state, it absorbs energy. Okay, when it goes from ground to excited. And then when it falls back down from excited state back to ground state, it releases energy as light. Okay, so we can see it. So if you did in lab, flame test lab, that's when you saw it. The electrons absorbed energy because you heated them in a flame, but they don't stay up there for too long. They fall back down and release energy as light. And then a flame test, we see it in color. We see it in fireworks as well. Okay. Okay. Okay, so I absolutely hope that you do get to your 80. That would be awesome. Okay. Oh, 64, that's brutal. And neutralization. Do I only have to remember about it being acids and bases? Okay, so yes, neutralization is definitely, you should remember it is, you should remember it's acid plus base yields water plus salt. Okay. There was a question on the exam. So I'm going to go to June's exam because the question was a little different than previous questions right here. Okay. So let me just make this a little larger. Right here is 64 and 65 from this exam. For 64, it says, write the name of the laboratory procedure used in this activity. Okay. Let me know what you are trying to memorize, and I'll see if I can help you. I mean, I can't help you put it into your brain, but I might have some tricks to help you remember something if there's something in particular. Okay. So for this one, for 64, so many people got it wrong. Okay. The name of the procedure. Now, laboratory procedure examples would be things like evaporation, distillation, chromatography, filtration, And then this one, titration. Okay. They're not going to ask about many laboratory procedures. That's kind of it. These four all deal with ways to separate mixtures. So that's a common laboratory procedure. Okay. And this one right here, now there was a little bit of a hint in the question. Okay. So it said you had an acid, it said it was neutralized, and then it said sodium hydroxide, which is a base. If you knew what formula you had to use for 65, then when you look at the reference table, so I'm going to scroll to the reference table. This is the formula, and there is the name of the lab procedure. Okay, so it was a strange question. Most people wrote neutralization for the question, but that's not a lab procedure. That's just like a process. The lab procedure itself is titration. Okay. And then all you had to do for this one is plug it into this formula, and you didn't even have to solve because the question said show a numerical setup. So you just had to put the volume of the acid, the volume, and the molarity of the base in the correct spot, and that's it. Okay. I know it was a tough question. All right, so memorization for like equations. Do you mean like balancing equations, or do you mean for the types of equations? I think you must mean types of equations, right? I can kind of go through some hints I have for that. I think that's what you mean. Okay. And I see your question. How do you evenly distribute elements for what do you, in like what context? For like writing a chemical formula, for balancing an equation? Let me know for that. And then I'm going to go through some types of equations. Okay. Oh, for sure. It is absolutely taught overcomplicated. I try not to. I mean, I don't know if any of my students are here, but I try not to teach it overcomplicated. Okay, so yeah, I can do balancing too. Okay, and the balancing from the exam was probably the hardest one that I've seen in a long time. So we'll do that one. If you can do that one, you can do any one that they can throw at you. Okay, so first I'm just going to do some types of equations. All right, so I'm going to go here. I have some blank space. Okay, so there are kind of two sets of equations, all right? So we have types of equations, and then we have, or types of reactions, and then we have types of organic reactions, okay? So for the types of equations, we have decomposition. Okay, when things decompose, they break down, right? So decomposition means breaking down. So that means I take something that is connected together, like AB is bonded together, and I break it apart into A plus B, okay? And then I have synthesis, and synthesis means to build. Okay, so this is going to be the opposite of decomposition. So I'm going to have A plus B combining to form AB. All right. Then I have single replacement. Okay, so what I'm going to say right here is AB is connected together. Think about it. A and B are dating, and C is single. Okay, so that's what's happening. A and B are in a compound, C is a single element. So A and B are dating, C is alone by itself, okay? What happens in single replacement is they swap places. So now A and C are dating and B is alone, okay? And so that's a single replacement, okay? You are welcome. And then double replacement is where we have two sets of compounds, A plus B and CD. Okay, so this is like A and B are dating and C and D are dating. And then there's a total swap. There's two swaps. It's double replacement. Yep, exactly. So double replacement is two of them. So what's going to happen is what I have to notice though is A came first in the formula. So A will stay first. But instead of being with B, A will switch to D. Okay. And then C came first. So it will end up looking like this. Okay. So, but it's still a swap, right? They swapped partners. So single replacement is there's one swap, double replacement, two swaps. Okay. Also, another trick to remember it is single replacement. Yeah. Has a single element. So to see how as an element alone, single replacement, okay? Single replacement reactions are also always redox, reduction oxidation reactions, okay? All right, so that's just the general types of equations that they could ask about. If they ask about organic reactions, that's a different set of equations. Okay, so I teach this faces. Okay, that's what I teach for remembering the organic reactions. Okay, so I'm going to go through each one. All right, so P is, let me just go a little smaller here. Polymerization. Okay, so polymerization. Polymerization means building a big molecule, a polymer, huge, a big molecule. Okay. Yeah, so I'll do that next. Okay, I'll do the types of organic reactions. I'll do 58, and then I will do the balancing equation question. Okay, so S is saponification, and the first four letters of saponification are soap but scrambled. Okay, so that's how we remember it. Fermentation is making alcohol. It also makes CO2, so it makes bubbles. So think about beer or champagne. It makes alcohol and bubbles. Yeah, exactly. Saponification and soap. A is addition. So that needs an alkene. So it has a double bond. So you break the double bond and add two atoms. So addition, you're adding two atoms. Okay, so that's the A, addition. C is combustion, which is burning. Okay, so that's with oxygen, and you get carbon dioxide and water. E is esterification. That's making an ester. Check table R for the functional group for an ester. All right. And then lastly is substitution. And substitution is a swap of one element. So I take one atom off and I put a different atom on. Okay. And just as an aside, I do have the video on, but if you let me know if it is laggy, I will just turn the video off. Okay. I'm trying to keep it on, but if it is laggy, I will shut off the video. Okay. So definitely let me know if it's having an issue. Okay. So there are the types of reactions. I hope that helps. All right. So I'm going to go back to 58. And then I'm going to do the balancing equation question. Okay, so 58. Okay, so I have this question set about this reaction at equilibrium right here. Okay, it says it can reach equilibrium. Okay, so I see your covalent intermolecular. Well, now you do know what saponification is because that was a multiple choice question. I'm going to go through a balancing way and we'll see if that helps you. Okay, so yeah, I'm going to get through these questions. So 58 balancing, and then I'm going to go through covalent intermolecular, and then 18. So this was June's exam, June 2023. That's the exam I'm looking at. Okay, so it says compare. When you get a question that says compare, there are only 3 possible answers. So if it's a compare question, you should always guess, even if you have no clue, because the only 3 options are the 2 things they're going to talk about are equal, one is greater, or one is less. That's it. Those are the only 3 options. Okay. So when it says here, compare the rate of the forward reaction to the rate of the reverse reaction when the system is at equilibrium, my only option are the rates are equal, the rate of the forward reaction is greater, the rate of the forward reaction is less. That's it. Those are my only options. So this is just a remembering it question. And when a system is at equilibrium, rates are equal and concentrations are constant. So do you see how it starts with concentrations are constant? Oh, do you mean this equation right here? What does this mean? Okay, so I can talk about that. So this is remembering that when a system is at equilibrium, rate of the forward reaction and the rate of the reverse reaction are always equal. Okay, so what this equation means is this 2 in front of the NO2 means there's 2 moles of NO2 gas. This has right here has arrows in both directions. So that means, well, what this means, I know it kind of looks like an equal sign, but what it means is that you have 2 moles of NO2 gas going this way and forming N2O4 and releasing energy. And then you also have the reverse reaction occurring. That means energy is being added to N2O4 and producing 2 moles of NO2. Okay, so you have what this weird looks kind of like an equal sign is. It means that there's a forward and a reverse reaction happening. Okay. Yes, to answer your question, absolutely. You would have gotten credit for this question if you just wrote equal. If you literally just the word equal, if you just wrote the word same, that you would get full credit. Okay. You could write out a lot of words like the rate of the forward reaction is equal to the rate of the reverse reaction, but that's not necessary. You could say rates are equal or just plain old equal. If the answer was something else, like one had to be greater, then you would have to say which one is greater. But if they're equal, you can literally just write the word equal. That's it. Yes. So the answer for 58 is simply that they're equal. Okay. That's it. And that's just a remembering. Yeah, I know, especially when I looked at how many compare questions. So I'll just show you if I can search it real quick. Compare, there were 7 compare questions. So those give you 33% odds of getting those questions right because the only options are equal, greater, or less. Okay, so that's a lot. So even if you have no idea what the question is asking, they literally tell you to compare. They tell you the 2 things to compare. So at the very least, guess. Okay. Okay, so I hope that helps you with question 58 because that was somebody's question. All right, now I said the balancing equation. So I'm going to go to the answer booklet for this one because that's where the equation is. And here it is. Okay, so, and I'm going to show you the tip that I use to balance an equation. Okay. And once I do this one, I am going to go through and check for the other questions. I know next it was covalent and intermolecular, and then I'll go forward from there. Okay. So if you have a question, definitely put it in chat. I am going to go back and get as many as I can. Okay. So if we look at this question right here, all right, to balance. Okay. If I just do a quick check, okay, I can see that I have on this side of the equation. So this is how I like to do it. I'm going to make a list of elements, N, H, and O. Okay. Divide. And then on this side, I also have to have N, H, and O. Okay. But look at this. See, in a bunch of ways, this was a terrible one. See how O is in two places? Okay. So I'm going to divide it like this. So now I'm just going to count. I have 1 nitrogen, 3 hydrogens. I'm looking at subscripts. That's it. 2 oxygens. I have 1 nitrogen, 2 hydrogen, and then I have 1 oxygen right here and 1 oxygen right here. So that gives me a total of 2 oxygens. Okay. Yes, I know. I see that we are hopefully helping get ready for the exam tomorrow. Okay. So I'm doing my best to help with that. Okay. So when I look at this, nothing, what is wrong is hydrogen, right? Hydrogen is not balanced. Okay. But I'm going to go for a rule that, or at least a strategy to help you balance an equation that if you are stuck, it can get you to the right answer. Okay. So what I'm going to do is start by, and I'm going to switch colors here, and I am going to put a 2 in front of the formula that has, I'm going to ignore the side where oxygen is split. Okay. And I'm going to put a 2 in front of the thing on the other side that has the most stuff. Okay. Yeah, you could just write it as, oh, it's 2 for that. So I'm going to put a 2 in front of here. When I do that, I multiply nitrogen times 2. So that gives me 2 nitrogens. Hydrogen times 2, because I distribute. Well, why did I put this? Okay, so I put this 2 in, meaning I have 2 of these. So my chemical formula of NH3 only has 1 nitrogen. So I have to now multiply it by the coefficient, okay? But that coefficient has to get distributed to everything in the formula, okay? So this would be 6, right? 3 times 2, right? Yeah, so on the other side, to balance the hydrogens, right? Okay. I would put a 3, right, in front, because I want it to equal 6. So times 3 on that side. Yep. So that's going to be 6. Okay. That 3 also affects this oxygen, right? And then here is where I notice a problem. Okay. Why did I put the... Oh, why did I put that little caret sign? Oh, okay, I see what you're saying. The reason is oxygen is here in one formula, but oxygen is also over here. So if I put a coefficient here, for example, it only affects this oxygen. And a coefficient here only affects this oxygen, but I need to know the total number of oxygens. And so this is just a reminder that oxygen is in 2 places. And this side is a reminder that I have to add them up. Okay. I hope that answers your question about what I was doing there. Okay. So when I do this, right? Okay, let's just fix it. Let's fix the nitrogen. I noticed the problem right away, but you might not. So let's just do this. Okay, that fixed nitrogen, right? Put a 2 here. Okay, everything is looking okay so far. So that is what this was here, right? Now that 2 also affects this oxygen. Okay, but I see you say, wait, and if you explain, if you say what you're confused about, I will try to explain it. So let me just go over what I have so far. I started by putting a 2 in front of this because it was on the side where oxygen wasn't split, and it was the thing that had the most elements in it. Okay, this 2 gets distributed to everything in the chemical formula. That's why everything is times 2. Okay, on this side, I multiplied nitrogen times 2, so both sides would equal 2. On this side, I multiplied hydrogen times 3, so that both would equal 6. Yes. Now, this is where the problem is. Okay, so what is 3 plus 2? Right? Because the oxygen is split, right? So 2 oxygens are here and 3 oxygens are here. That gives me a total of 5 oxygens. Well, this is where I have a problem, right? Yep, awesome. You see that's 5. I cannot multiply 2 by anything and get to 5, right? This is not possible, right? I have to use whole numbers. Physical, like just to answer, quick aside, topic always on the Regents, physical behavior of matter. So endothermic, exothermic, changes of state, those kind of things. That's like the biggest section that is always on the exam. So when you are doing this, like sometimes balancing is just trial and error, okay? So what I would do is be like, I can't make this work. And so if you don't know what you're doing, you literally start over. But it's like with a system, okay? So remember how I multiplied by 2, right? Before? You need about 50 or 51 out of 85 points in order to pass. So I am not going to put a 2 here. I'm going to try a 4. So balancing is trial and error, which is why I say this was the hardest balancing equation I've seen on an exam in a long time. Usually when you try the 2, it fixes it, it works. But it didn't work in this case. So when it doesn't work, it is a lot. Compared to other exams, absolutely 50 is a lot of points. So I'm going to multiply by 4, okay? So remember how I multiplied by 2 here? Right? And this is the only reason I switched colors. So I'm going to multiply by 4. Okay. All right. Which means this also gets multiplied by 4. I don't know. It was very unusual to see the balancing be this hard. So I would hope that they wouldn't do a hard one like that again. Now I'm going to go to the other side. So remember, like if this was pencil, I would just erase it. I just don't want to erase it because I want you to see what I'm doing. Okay. So instead of this and this, because I'm restarting, right? Yes, you're just making both sides equal, right? So on this side, I have to multiply the nitrogen times 4, right? So I'm going to write that one down. What do you need to multiply the hydrogen by? Okay, so the nitrogen I'm multiplying by 4, right? So that's this first oxygen, right? What do I need to multiply right here? What do I need to multiply the hydrogen by? So think, I need to end up with 12. Yep, exactly. I have 2 already, so I multiply it by 6. That is going to give me 12. Okay, so a 6 goes here, right? When the 6 goes here, it gets distributed to the hydrogen, which is what I wanted, but also to that oxygen. So times 6 is 6, right? Because it was a 1. Now what do I get when I add? 4 plus 6. I get 10, right? 4 plus 6 is 10. Now, what can I do this? Can I multiply 2 by something to get 10? Can I do that? Yep. So I have 10 oxygens. What can I multiply that 2 by to get to 10? Can I do that now? Yes, absolutely, right? I can. I need to multiply it by 5. So that 5 becomes perfect, becomes the coefficient in front. Now I finally have it balanced. Okay. This is literally the worst case scenario. Okay. So my tip is this. If you have no idea how to start balancing, put a 2 in front of a formula that looks complicated, that doesn't have like a split element. Okay. If the 2 doesn't work, you could try a 3, a 4, or a 5. Like if you really are just doing trial and error, 2, 3, 4, 5. One of those absolutely 100% will work. Okay. That's so funny that your instructor was confused. I saw is chemistry easy or intimidating? It is a little bit, I think, intimidating. There is a lot of vocabulary, but the interpretation and understanding is a little bit affected by how much vocabulary there is. Okay, good. I'm glad balancing is easy. This was literally the hardest one that I've ever seen on an exam. So you are set. If they have a balancing equation, it probably will not be that hard. So you will be set and ready to go. All right, so I'm going to go back. I know it was covalent and intermolecular. I remember that part next. So I'm going to do that, and then I'm going to go back to where other people had questions. Okay, so there are, in terms of bonds, okay, so we can have ionic bonds. That's metal and non-metal. Okay, we can have covalent bonds, and they can be polar and non-polar. Also, fun fact, covalent equals molecular. So those two words they like to use interchangeably. Okay. Good, excellent. So see, I don't think balancing is super hard. It is just a matter of having like a little bit, like being able to sustain it. It's just trial and error. Okay. Well, I do understand having it after lunch. That can make it a little bit harder. And then the last kind of bonding is metallic, and that is just single metal elements. Okay. So. Oh, and I forgot to say, covalent is 2 non-metals. And the 2 types of covalent are polar and non-polar. And covalent also is molecular. So metallic is single metal elements like copper, aluminum, calcium, etc. Okay. So those are bonds. Okay. So ionic bonds. All right, so I'm going to get to polar and non-polar. Okay, so ionic is electrons, and fun fact: always write E. If you mean to write electrons, write E with the negative sign. Okay, so electrons are transferred. In covalent, all right, electrons are shared. Okay, and in metallic, electrons are in a mobile sea of electrons. Okay. And that's why they conduct electricity, because electrons are willy-nilly, loosey-goosey floating around. Okay. So that's for bonds. Okay. Yeah, it literally tells us in the answer key not to give credit if you forget the negative sign. So if you want to abbreviate electrons, you have to write E with a negative sign. 72 was that the 71 was the balancing. We didn't do 72 yet. I'm going to scroll back and look at which one was next, but I want to finish this for bonding. So how am I going to know if it is polar versus non-polar? That I need to know electronegativity difference. Okay, so electronegativity is on table S. And if it is non-polar, the difference is very close to 0. Okay. So less than 0.5. Okay. And polar means the difference is like between 0.5 and 1.7. Okay. And ionic would be the difference is greater than 1.7. Okay. So those are bonds, and these are intramolecular. They hold molecules together. Electronegativity is from table S. So since I did just talk about it, if we look at table S, I'll look at this one in particular. Electronegativity is right here. So it's just a value right here, basically just a scale. Fluorine has the highest electronegativity, and all of the other electronegativities are kind of based on the strength of fluorine. Okay. So yeah, this bold line is just separating into groups of 5. This electronegativity dash is by helium, because helium is a noble gas and it doesn't attract electrons. Neon, noble gas, and it doesn't attract electrons. I see the questions coming in. I will get to them. I do just want to finish this. So these bonds all up here are intramolecular. So what is intermolecular? Okay. Those are like, you don't usually have to remember the names. They just talk about intermolecular forces. The one you have to know the name of is hydrogen bonding. And that involves hydrogen with nitrogen, oxygen, or fluorine. Okay. What you do have to know is strong intermolecular forces equals high boiling point. That's really how they test it. Okay. So intermolecular forces are the forces between molecules, and intramolecular forces are bonds that hold molecules together. Okay. So think about it as the bonds that hold water together versus the bonds that connect two waters. Okay. So that's kind of the difference between them. Okay. I can definitely do that. I'm going to go back to up here. Let's see. I did this one. Balancing, double replacement. Yes. I missed this question before. I teach regular just Regents Chemistry, not honors chemistry. Did we do 58? Let me go back to it and see. Yeah, we did 58. Okay. And we did covalent. We did balancing 18. All right, so let's go look at 18. That's the next one that I had jotted down up here. Okay. In chemical reactions, which term is defined as the difference between the potential energy of the products and the potential energy of the reactants? Okay, so this is a very wordy way. Okay. Anytime it's potential energy, I am a diagram drawer. So I'm going to draw a diagram. Okay. And the diagram that I'm going to draw. Oh, well, thank you. Yeah, no, I just teach regular chem. I'm glad that I try to be a good teacher most of the time. I mean, I always try to be a good teacher, and I think usually I am. If students are doing the work, if you're doing the work, it's gonna translate to doing well. So I'm gonna just draw a potential energy diagram right here, so I can visualize it, right? As soon as it says potential energy, products, reactants, okay, I'm going to visualize it, but I want to see it on the paper, so I'm going to draw the diagram. This is reactants. This is products. So the question is asking me which term is defined, and this difference between products and reactants is defined as, and you're right, it is on the reference table. If you remember, there's a reference table you look at for potential energy diagrams, and it is this table right here, table I. So you can use table I to draw potential energy diagrams. And the literal title is heats of reaction. So what it's telling you, and at the bottom, it says this, a minus sign indicates exothermic. Okay. So that means any one that has a minus sign is exothermic. So it would look like mine did. Starts high, ends low. Okay. If it has a positive sign, like this one right here, it would be endothermic. And so it would look like this. It would start lower and end higher. Okay. So heat of reaction is always, this is just a definition question. I would just put a diagram to remind myself. The heat of reaction, or delta H, is always products minus reactants. They have to go in that order so you get the right negative or positive sign. Okay. All right. So that was 18. And 81. I thought it was like the same. Okay, 81. Just to ask for this one as I'm going to 81. Entropy, question 60, that's where I'm going next. Okay. So identify the element in the product of the reaction that allows it to be classified as an organic compound. Oh my goodness, this is so wordy for honestly what it should have been just a straightforward question. So first, this is the product. Okay. So identify the element. So the only elements I see are carbon, hydrogen, and oxygen. So my answer has to be one of those. Okay. And what allows it to be, I'm sorry, I didn't give the answer to 18. I'll go back to it. What allows it to be classified as organic? Now, it is carbon. Carbon is the answer. Now, in reality, carbon is almost always bonded to hydrogen, but you did not get credit for hydrogen. Why? Because without carbon, it can't be organic. Without hydrogen, technically there's, a scenario where that could be it. So the answer for 81 had to be carbon. So the element that had to be present for it to be organic is carbon. So yes, for 18, it is 2 heat of reaction. I see someone else answered that for you, but just to make sure, it is 2. Okay. And then I said I was looking at 60, which was having to do with entropy. I think. Was it 60? Yeah. Okay. So again, this is a second compare question. Remember, our answers are either going to be equal, greater, or less, right? Those are our only options, right? Equal, greater, or less. So what are we comparing? Entropy of a sample of dinitrogen tetroxide gas at 25 degrees Celsius and 1 atmosphere to the entropy of the same sample of tetroxide liquid at 15 degrees Celsius. Okay. So yeah, that's a good help to think that we're organic and we are composed of a lot of carbon. That's how we figure out how old bones are, right? From carbon 14. So what is entropy? Entropy is disorder. Okay, chaos. All right. So think about if you are stuck in a question, absolutely, just to go off for a second, I absolutely would start looking at the titles of reference tables. Look at the hints, like the little asterisks at the bottoms of the reference tables, and start scrolling through them. You'd be surprised how much information is there. Okay. Yes, carbon 16 is the mass. Yes. It's the mass number. Not atomic mass, but mass number. So entropy is disorder. So if we think about the particles in a solid, the particles in a solid are real tight and close and organized, so they have low disorder. The particles in a liquid are a little further apart, so they have a little bit more disorder. but the particles in a gas are super far apart, right? So they have the most disorder. So if I'm comparing the entropy of a gas to the entropy of a liquid, which one has more entropy, or are they equal? Because those are my options, right? One of them has to have more or they're equal. Okay. So remember, in a solid, the particles are real organized, very little disorder. It is like, yes, the gas has more entropy. So how you have to write it is the entropy of the gas is greater, the entropy of the liquid is less. In some way, write that. Yep. So the entropy of the gas is more. The gas has more entropy. Okay. So you had to say which one has more. So you couldn't just say more because that's not specific enough. You would have to say the gas has more. Actually, that would be enough because we're comparing entropy for both. Yep. You could write that. Absolutely. That is perfect. You could write the gas at 25 is more than the liquid. Perfect. You could even just write the gas has more, and that would be enough. Okay. All right, so let me go back up here. I did 81, 60. I think 71. Yeah, that was the balancing one. I did that one. We did 18. And that was when we went through all the balancing. So that is good. Okay. Okay, so metal, yeah, metal and non-metal. I just saw that question. I'll just go through that really quickly. On the periodic table, this right here, this zigzag line that separates, on this side, we have non-metals, and on this side, we have metals with exceptions. So there are metalloids, and it is this one, boron, silicon, germanium. They basically have to touch the vertical, that vertical line. Oops, doesn't want to do this one. I guess I'll have to draw it. These two also, they don't usually ask about these two, but they would be considered metalloids. So those ones would be metalloids. Okay, so that's what those would be. Okay, I think the document is just being weird. That's the problem. So they would be metalloids. All right, I'm just going to reload this because it's being a little problematic here. Let me just see. Okay. All right, so that helps. Okay. Oh, I did this one. How do you figure out the names of certain? Okay, so now I think I'm on this one. Hopefully I did not miss any. I don't know why this is not loading. Let me turn this off for a second. Okay. So naming. I think I'll have to open it from my document here. So naming is most of the time they're going to have you naming something using table E. Table E is pretty common. Okay. So you should definitely know to look for table E. Okay. And oops, I don't want to do that. So when you look at table E, it's going to give you the name. So for example, you said nitrate. So how would I know what it would look like? Well, do you see right here, nitrate? And then it tells me what the formula is for nitrate, which is NO3 negative. Okay, so using table E is super helpful. Okay, so how would I then write the formula for if I was doing if I wanted to write sodium nitrate. Okay, so let me try and open this. Let's see if it'll open this way. All right, let me close this. I think Edge just decided to be problematic. So now I'll try and reopen it and see if that works. There we go. Okay. So table E. So you gave the example of sodium nitrate, right? So nitrate is NO3 negative. And I don't teach crisscross method because what happens is people crisscross the subscript, and that's problematic. Sodium I'm going to get from the periodic table. So let me just go there so I can show you. Sodium, if you don't know sodium symbol, then I'm going to go here. It's Na. Its atomic number is 11. And when I look at the oxidation state right here, I see that is +1. So I'm going to go back here. Na +1. Now, in order to form a compound, the charge has to be... Okay, so I'm going to answer your question about hydrogen really quickly before I finish that one, only because I don't want that to... I want to make sure I answer it. Hydrogen, you're right, is with the metals, but hydrogen is a non. The reason it's over here is because in terms of valence electrons, it lines up here, but hydrogen is a non-metal. Okay, it's the one exception. Just like aluminum right here, number 13, is not a metalloid, even though it touches this vertical line. Aluminum is a metal. Okay, so hydrogen is a non-metal. Everything else over here is a metal. The metalloids touch the staircase except for aluminum. Okay. All right. So I just want to make sure I cleared that up. Hydrogen is definitely a weird one. It is super weird. All right. So if I go back to what I was trying to do here, in order to form a compound, the positive and the negative charges have to balance each other. So if this is +1, right? And this is -1. If I add those together, will I get 0? Yep, absolutely. So how do I write the formula for sodium nitrate? I simply write NaNO3. I just smush the two things together and don't write the charge. Okay. But what if it wasn't so easy peasy? Okay. What if instead I had to write the formula for, let's say, aluminum hydroxide. Okay. See hydroxide right here? That's OH negative. Where's aluminum? Right here. Look for its oxidation state, its charge, +3. So let's go back to where I was. +3. So aluminum, +3. So now, remember, forming a compound, those charges have to be, you can do crisscross, I just don't teach it that way. I'm going to show the way I teach it. I teach just writing it visually. So you can, I don't like teaching crisscross because of subscripts like this in the polyatomic ions. But, and here's why. So aluminum has a +3 hydroxide, so I have 3 positives total on this side. But I only have -1. And if I add those together, I won't get 0, right? So I need more negatives. So I'm going to add another OH negative. That will give me -2. I'm going to add another OH negative. Well, that will give me finally -3. Now they will balance out, right? And I'll show you why I don't like crisscross in this case. So how many aluminums did I need to balance it out? 1, right? So I just write Al. What else did I need? I needed 3 of these, right? So OH in parentheses, because it came from table E, and put the 3 outside. Okay? What I often see when people crisscross is that they just put the 3 outside the hydrogen and forget the parentheses. So I just teach it visually like this so that students can see that you needed 3 of the whole OH thing. Okay? Okay, so something I've seen repeat on the Regents. Let's see. So if I go to some topics for the exams, so I will look at June just because I can point it out. You would have at least seen this one. Gram formula mass, that's definitely, usually that's on the exam somewhere. Calculating these two right here, calculating molarity, calculating parts per million, that's pretty popular. In some way using table G, that's for sure popular. Something with a potential energy diagram, see that all the time. This common question, this right here, pretty much a guarantee. In some way, they're going to ask this. Lewis dot is less common. These about Arrhenius acids and bases. This is super common for electrochemical cells. Okay, so those are some of the popular. Also, just atomic theory in general. Okay. Yeah, definitely where electrons are located. They love the orbitals. I'm going to get to some questions. I know you asked for some questions. Okay, so what happens to charge, mass, and energy in chemical? Yeah, for sure, that's another repeat question. Charge, mass, and energy are conserved. The way they asked the conservation of mass question on this exam was strange. This question right here. I have never seen it like this. This is how they asked conservation of mass. I also don't like how I cross it out. I circled it here. This question right here, have never seen it like this, but it was testing conservation of mass. Okay. And yes, I will do a gram formula mass. Okay, so I'll go over this question real quick. Was anyone confused on number 50? I can go over it. If you are, I'll do a gram formula mass in the meantime because I did just talk about that. Okay, let's do it for aluminum hydroxide because we just wrote the formula for it, right? ALOH3. Okay, you're welcome. If you have a chance, you can always check back in, what we go over later. Awesome. Yeah, definitely for sure. Let me know how this one goes. I hope everyone does amazing. And I know I said it would stay at least an hour. There's still questions that I haven't gotten to, and I still do have some more time. So I will stay longer to try to answer as many as I can. Okay. Oh, tell Bella I said hi. Okay, so gram formula mass or GFM. Okay. First, you figure out what elements you have. I have aluminum. I have oxygen and hydrogen. I jumped ahead to hydrogen. How many aluminums are in this formula? 1. How many oxygens are in this formula? Well, see this subscript outside? It gets distributed to everything inside the parentheses. So I have 3 oxygens and 3 hydrogens. Okay. Now how long will I be staying? We'll say at least another half an hour because I do want to try to get through all of the questions that I've seen pop up. So at least a half an hour. Okay. And then I'll see how we're doing at that point. Okay. So, I have the number of atoms, but now to do gram formula mass, I need the mass. So I need to go to the periodic table And I need this number, atomic mass, for each one of those elements, okay? So for aluminum, it's 26.98. I can round that to 27, okay? So 1 times 27. So that's 27, right? Oxygen, right here, 15.994. I can round that to 16. So 3 times 16, that's 48. And then hydrogen, if you look here, this I can clearly round to 1. So 3 times 1 is 3. Now, so what that means is when I look at aluminum hydroxide, 27 grams of the mass come from aluminum. 48 grams of the mass come from oxygen, and 3 grams of the mass come from hydrogen. So to find the gram formula mass, I add these up. Okay, so 7 plus 3 is 10, plus 8 is 18. Carry the 1, 4, 5, 6, 7. So 78 grams per mole is the gram formula mass of this compound. Now, I will review something else at the same time because they had a question like this. Yeah, so there's 3 hydrogen and 3 oxygen. Why? Because the formula, I know it kind of looks weird because I wrote afterward. The formula is this: aluminum within parentheses, OH with a 3 outside. So this 3 means 3 times everything that's inside the parentheses. So yes, that means I have 3 hydrogens and 3 oxygens. Okay, so 78 grams per mole is my gram formula mass. What they like to ask also is percent composition. So do you see this? Mass of part over mass of whole times 100. So if they said, what is the percent composition by mass of oxygen? Okay, so the formula is what? Mass of part over mass of whole times 100. Well, what is the mass, since they were asking for the percent composition by mass of oxygen? Oxygen is the part. The whole thing is the whole thing. So what is the mass of the oxygen part? 48. What is the mass of the whole thing? 70 times 100, because that's the formula. So if I look real quick again, mass of part over mass of whole times 100. So to find the mass of oxygen, the percent by mass of oxygen, it's the mass of oxygen, the mass of the whole thing times 100. So what would be different if I had to find the percent of aluminum? Instead of 48, it would be 27, but the whole would be the same. So it would be 27 over 78 times 100. And I would do the same for hydrogen. So that's just to go over gram formula mass and percent composition. So yeah, then you would just do this math and yeah, that sounds about right because that's about 50 over 80. So yeah, exactly. Okay. So I did say I'm going to do 50 because I mentioned it for conservation of mass because it was a bizarro question. Okay. So with conservation of mass, I'm going to show you in a simple equation like this. So here's a simple equation. If I had 10 grams of this and I produced 4 grams of this, right? How many grams of chlorine would be produced? Well, on both sides of the equation, the mass has to be the same. That's the rule of conservation of mass. So 10 grams on this side means I need 10 grams on this side. So how many grams of chlorine would I need? If I already had 4 grams that came from sodium, chlorine would contribute how many grams? Hopefully that math makes sense, right? Yep, exactly. So the chlorine would be 6 grams, right? So that's the concept of conservation of mass. So what they said here is, what is the, for number 50, what is the amount of mass converted to energy as a result of the reaction? So the reason nuclear reactions are so powerful is because literally they take some mass and convert it into energy. This is unlike any other reaction. So we get a huge amount of energy because some of the mass ends up being lost as energy. So if there were conservation of energy, of mass, so do you see this line right here? Add these two together. So let's just do that. I'll pull up a calculator here. All right, and we'll do 6.051, 0151 plus 2.0140 equals. So that answer, right? I'm going to copy that. That answer is those two added together. Okay, so do you see what I did? Okay, hold on. Why is it? Oh, I was just picking a random number for that question. For the 10 grams, I was just giving a very simple example on how we get to conservation of mass before we got to these complicated numbers over here. So I'm sorry, I just was picking a random number. It wasn't 10 from the question or anything, okay? I was just showing an example of how conservation of mass worked. So if I have 8.0291 U on this side, I should have what? I should have this, right, on this side. That's conservation of mass, right? They should be equal, okay? So do you see how this is 2 times that? Let's see what that is. 2 times 4.0026. It equals this. So let me just copy this over. So it was supposed to equal this, but it didn't. It equaled this. So the question is, what is the amount of mass converted to energy? So what do you think I need to do with these two numbers then? That means some of the mass isn't there anymore. It's energy now. So I would do what with these numbers? How did I get that? I just used these decimals that, I used these decimals that were here because they said I have, yep, you're right. So I had this number plus this number. That gave me this. Yep, exactly. You are right. I'm going to subtract them. So this plus this gives me this. So I should have had this answer over here. But when I multiplied 2 times this, I got this answer. And these are not equal, right? Which means some of the mass got converted to energy. So subtract them and you end up with this. Okay? So some of the mass disappeared. Now, in reality, you should have been able to answer this question without even doing the math. Yes, exactly. The U in the choices. So the reason is a little bit of mass is converted to energy. So if I were just looking at this question, I would automatically assume that the smallest number was correct unless I proved that it wasn't. So I'm looking for a tiny number because it's not a lot of mass. It's really, really tiny, but it's big enough that it creates a huge amount of energy. Okay. And then I did see, because we talked about nuclear here, nuclear fusion and fission. Yes, fusion is you take 2 little nuclei and make one. And fission is where you take 1 big nucleus and split it apart. Yep, you are right. Okay. Let's see. So yeah, that was a very weird question, just to test conservation of mass. So again, I don't know, that was a bizarro question. Yep, exactly. You're right. You subtract 8.0291 minus 8.0052 to get the answer. Yep. You want to find the difference between what you were supposed to get and what you actually got. Okay. Yes, fusion and fission are both nuclear and both release a huge amount of energy. So the names they could give to nuclear reactions, the names that you might see that mean nuclear, are fusion, fission, natural decay, artificial decay, and transmutation. And those all mean nuclear. No, 8 points. I'll show you again where I got the 8.0052. You're fine. Okay, so do you see how here, I'm going to just erase this part that I wrote here. Do you see here how it shows that right here, there's 2 of these, right? So this 2 in front means there's 2 of that mass. So I literally just did right here, 2 times 4.0026. And that's how I ended up getting the 8.0052. And you're not slow. It's fine. This is a lot. It's a lot to try to absorb. You are okay. All right. So 8.0052, that's where that came from. Multiplying the 2 times the 4.0026. Okay. Okay, so besides the balancing, what else was pretty hard on this exam in particular? Okay, this was not a hard question, but so many people got this one wrong. When it says state the direction of heat flow. Oh, for the Jiminy Cricket. Don't say up, down, left, right. No. North, south. No. When we're talking about heat flow and the direction of heat flow, you're going to say it flows between or from which thing to which thing. So they're going to mention 2 items, and you're going to say that the heat flows from which thing to which thing. Okay. So it says, no, you're only going to get 1 exam grade on your transcript. So you could take it as many times as you want and just your highest grade will show up. No one's going to know if you took it once or 5 times. Okay, so don't stress about that. Okay, so state the direction of heat flow between the candle flame and the beaker of water. So what do you need to know about heat? As an aside, heat flows from warm to cold. Heat flows from warm to cold. Okay, so that means that heat flows from high temperature to low temperature 100% of the time. Do not say up, do not say heat rises, do not say down. No, you say heat flows from warm to cold. In this case, you get to figure out which one is warm and which one is cold. Okay, so obviously, this should be fairly obvious. You have the temperatures here for the beaker of water. So heat is going to, you could take it whether you fail or pass. You could just keep taking it. That's up to you. Some people take it again to try to get mastery or get the 90 because they want to get the either advanced designation or with honors. So you can take it as many times as you want, whether you passed or failed. Okay. So since the candle flame is warmer, it flows from the candle to the water. So you could say from the flame to the beaker, from the candle to the water, from the candle flame to the beaker, from the candle flame to the water, something along those lines. Do not say it flows up, down, sideways, left, right, north, south. No, always, because what I could do, I could put a heater directly above my head. And the heat would flow from the heater to me. So it would flow in a downward direction. So we never want to talk about like heat rising because heat always, the rule is it moves from warmer to colder. Okay, so the warmer thing, it goes to the colder thing. Okay. So like if I open the door and my house is warm and it's cold outside, the warm air from my house will leave and will flow out to the cold. Okay. If you said from the candle to the beaker, yes, absolutely. From the candle to the beaker would count. Yes. So yeah, absolutely. So what will happen is heat flows from the warmer thing to the colder thing. So the colder thing starts to get warmer because the heat moved to it. Okay. So then that is why, if you look here, the temperature of the water started here and ended here. Okay. So the temperature increased because heat was flowing to it. So the thing that got higher in temperature, heat was moving to it. Okay. So this was, again, a simple one that a lot of people just got wrong. And so they lost that point. Okay. Yeah. If you said heat to the water, you would be okay, because it only mentioned the flame and the water. So if you said to the water, that's okay. That's enough of the information. And you said heat was moving. So yeah, you're fine. Yep. That's absolutely, you would be 100% right for that. Okay. So 60, that section for 61, 62, 63. Oh no, this is where I was getting next. This is these were the hardest questions. Okay. First of all, I have a real issue with number 62. So, feel some type of way about how they were grading this one. So I'm gonna talk about it. Yeah, I know some, just to answer, some schools make students take it multiple times. And it can get incredibly frustrating, but hopefully people do wonderful tomorrow. Okay, so I'll be thinking fantastic thoughts for you tomorrow as you take this exam. Okay. State the change in oxidation state of copper in this reaction. I'm gonna show you what my issue with 62 is in a second, and why I feel some type of way about it. But 61, 63 is the hardest question for this set, but 61, still a lot of people got it wrong. Okay. So when an element is like this, see how it's alone? Not in a compound, and like this, not in a compound, and how there's no charge. Like it doesn't say this. It doesn't have a charge written up there. So this oxidation state is 0, and this oxidation state is 0. Okay. Now I need to know the oxidation states for here. Now what I'm going to do is this 2 is just used to balance the equation. It does not affect oxidation state. So I am going to suggest that you cross it out so that you don't get confused and try to use it. Because trust me when I say it gets used and people mess it up. Okay. So do you remember I looked up nitrate on table E before? Maybe. And it was -1, right? So, and I have nitrate over here. That's also -1. Okay. I need that to help me figure out the oxidation state of Ag. So NO3 is -1. If I have 1 Ag combined with that NO3, then what is the oxidation state of this Ag? Well, it's going to be Ag plus 1. So in order to balance it, right? Oops. That looked terrible. So this is Ag plus 1. Okay. Now let's look over here. See this 2? What does that mean? I have 2 NO3s. So I don't have -1. I have -2. So if I have 1 copper, right? the copper has to be positive too. Okay, so you had to use the NO3 to help you. The NO3 is something that is called a spectator ion. That means it is present in a compound on both sides of the equation, so it's not involved in redox. So typically we just cross it out. But before you cross it out, you have to use it to help you figure out the charge or oxidation state of the other thing. Okay, so when it says state the change in oxidation state of copper, let's look at what the answer booklet looked like. Let me go to my exams. June. So when we look at the answer booklet for this question, it looks like this, from blank to blank. So copper started as what? 0. What did it end as? +2. So that's your answer for 61. Okay. Now, 62. Again, I told you I have a little bit of a beef with question 62, and I need to pull up our rating guide to show you why. So for this question, all right, so let's go to the, based on table J, perfect. Look at table J, like that was a gift wrapped up in a bow, okay? So look at table J, perfect. And then it says, state why CuS reacts spontaneously with Ag plus aqueous. Okay. Yeah, I can go over it again, but I'll erase it and go over it again. Let me do this one and then I'll go back over it. Okay, so why Cu reacts with Ag plus. So here's say Cu, here's Ag. Now what I want you to notice is that there are no plus signs written on table J, right? No plus signs. You just see the names of elements, right? So for this question, based on table J, why it reacts, I have to say copper is higher. That's enough. Cu is higher. Cu is more active. Yes, absolutely. Cu is higher. But here's why I said I have an issue with it. Look what they did not allow. Do not allow credit for Cu is more active than Ag plus. You see the plus sign? They literally told us we couldn't give credit. Now, why do I have an issue with it? Because that is literally restating the question. And I have a real problem with that. So it literally said, do not give students credit if they simply rewrite this question. And that was very frustrating from a grading point. So what I want you to, this is why I'm going over this question. It really is not fair. We hated it. Almost everybody lost the point. I'm going to be honest. Okay. Pay attention to table J. Table J does not list any charges, right? You see no plus signs. So that means table J does not allow me to talk about plus signs. So I can just say copper is more active. Silver is less active. Copper is more active than silver. Okay? And they just didn't want you to put the plus sign because table J doesn't mention plus signs. It's a little mean and a little petty, which is why I feel some type of way about it. I didn't really like it. And probably for every 10 papers I graded, 9 people got it wrong. And 7 of those people wrote this. So frustrating from a grading perspective. Okay. All right. So let me go over this oxidation state again. So I'm going to do that first before I do 63, because 63 kind of relies on 61. So I'm going to erase this and go over it again. Okay. Okay. Yes, as long as you did not say the plus. So I guess what we've learned, and I did not know they would ever be this petty. What we've learned is that when you're talking about table J, never mention charge. Plus signs, minus signs, nothing. Just either use the symbol of the element or the name of the element. So that's it. Okay. Okay, so let's look at this. So I know you said that you were confused. I'm going to run through this again. First, any element that is alone. How do I know it's alone? Do you see how it's not in a compound? Okay. And it doesn't have a charge. You see how I wrote an example right here with a charge out here? It doesn't say that. Yes, they did give credit as long as if you just said AG, CU is more active than AG, that was fine. As long as you left off the plus, you could not have said the plus. Again, mean as heck because literally that's what it says in the question. It was a little bit rude, okay? No, and you're not all failing tomorrow, okay? You will be surprised how much information is on the reference tables, okay? And if you're stuck, look at the reference tables. Even look back at a multiple choice question. And remember, never leave a compare blank because remember, there's only 3 possible answers. But, okay, here, Cu, no, it is a single element oxidation state of 0. Ag, single element oxidation state of 0. Okay. Now, when I look here, no, I do not accept. You have to have a more positive mindset. I will do the best I can. Maybe I won't get to passing on this one. You never know, but you try your best. Mindset is a big piece of it, though. Okay, mindset is important. So go in with a more positive mindset. Okay, and you will be surprised if you go in thinking negative. A lot of times, that affects how you do. Well, you also, fun fact, the August exam tends to be the easier exam. It's not always the case, but it tends to be the easier one. Okay, so you should be think pass, not fail. And whether you have to take the course again depends on your school. So that would be a guidance question. Okay. So I'm going back to here. Do you see how nitrate right here has a negative charge right here? Okay. So you see how I have nitrate that has a negative. But do you see this 2 outside? I guess they're making sure that you take it if they keep calling. So yes, again, August tends to be the easiest exam. Statistically, tends to be the easiest. Okay. And positive mindset. That's important. Those two, like just thinking about those 2 things, it may influence how you do on the exam. So don't go in thinking you'll do badly because then you will just kind of it will end up you may just making that come true. Okay. Okay. So, and then you see this 2 outside the NO3? That means there's 2 of them. So 2 NO3s. Okay. So this one had a -1. This one had a -1 for a total of -2. Okay. You're welcome. See, and then hopefully I will get great news from you and you say, I did better than I thought I was going to do. That's the news that I love to hear. Okay. So I did better than I thought I was going to do. So have a mindset that you're going to do okay. All right. And go in and say, I am going to do my best. And if your best means you got an 83, then that's awesome. If your best means you just barely passing at a 66, beautiful. Okay. I know. Geometry too, it's rough when you have multiple exams. The summer school schedule is so smushed. Okay. So -2 is what I have for the negative charge. So that means I have to have +2 to balance it, right? Because -2 and +2 gives me 0, right? So, and I only have copper here. So that means copper has a +2. Okay. On this side, I have also NO3 again. So it has a negative, but I only have 1 of them. So it's a -1. What do I need in order to balance a -1, a +1? I'm so glad that it has been helpful. Okay, so good night, good luck. I hope you do amazing tomorrow, and I can't wait to hear about how you do. Okay, so good luck. And so that means, awesome. That is so good to hear. I'm so glad that it's helping you. So that means that since I only have Ag in the formula, the Ag is +1. Okay, so I did the balance equation one earlier, but I can run through another balance equation one once I finish 63. So Ag is +1, Cu is +2. So the change in copper's oxidation state went from 0 to +2. Okay. Now, this question, 63, it's probably the hardest question they could ask about redox. And so I need to go to the picture for a minute. Also, they didn't even give me a picture here for this one. So write a balanced half reaction equation to represent the reduction of the silver ions to silver atoms. Okay, so what I'm going to do is use that equation and pull out everything related to silver. Is Cu silver? No, skip it. Is Ag. Now, I said this before, but I'm going to say it again. This too has nothing to do with the redox. It's just balancing the equation. So I'm going to leave it off because it's going to make my life simpler. Okay. So yeah, when because I'm going to open up another Regents and look for a balancing equation question. So yes, I will give you some time to do some of those questions. Okay. So for this one, I am going to look at just Ag. Okay. So Ag is right here, +1. There's the arrow. And then Ag on this side with a 0, no charge. It is reductionist cathode. So there's a few phrases to help you remember, but what I'm going to draw here is a baby number line, 0, 1, -1. And I'm going to draw an arrow going this way and an arrow going this way. Now, electrons have a negative charge, right? So if I gain electrons, I get more negative. So that's moving this way on the number line, right? So that's gain electrons reduction. So moving this way would be Leo. Sorry, that L kind of went into the line. Leo, which is losing electrons. Okay, so gaining electrons, I get more negative, go this way. Okay, so let's look at what's happening to silver. Silver started with a +1 right here and went to 0, right? So you can see how it is reduction. It already told me that, right? But here is why drawing this little number line and this arrow is important. You see this arrow literally points this way. It says, excuse me, when you write a half reaction, please put the electrons on that side. Okay, this is June's exam. So put the electrons on this side. How many electrons? Well, from +1 to 0 is 1 electron. So plus electron. That's it. Remember how I said electron, when you write the E, you have to put the negative or you will get it wrong, right? So E negative, you have to write the negative. It literally tells us in the answer key, do not give credit if you forget the negative sign, okay? So you have to write the negative, okay? So E with a negative sign, okay? And then now that's it. That's the half reaction. That's the whole thing, okay? So let's find a, yes, all electrons are negative. So anytime you're writing a symbol for electron, never just write E negative, always. always write this for electron. Okay, don't ever write it without it. They literally say, don't give credit for this. Okay, let's see. I'm gonna pull up this exam and oops, that's okay. First, let me see if no, this one, oops, just this one. That January exam did not have balancing, so let's look at this June exam. Also, an electron is getting, well, if you lose electrons, it gets more positive. Yes. Okay. This one does have a balancing one. So let's pull up the answer booklet. All right, so it's this one right here. Okay, so this equation that you had to balance, is that the one? Oh, January 2020. Okay, I can. Short answer, in general, it's not, they're not as complicated as you often think that they are, to be honest. So if I look at this exam, just in general, this was last June's exam, okay? First, state the number of electrons. That's literally what is the atomic number, right? They ask this question all the time. Also, it's a compare question. Compare means it's either equal, greater, or less. The energy of an electron in the first shell to the energy of an electron in the second shell. The second shell has more energy. Second shell, third shell has more energy than the second shell. A higher energy level has more energy, okay? Okay, atomic mass. I'm going to leave this question here, okay? But I'm going to go back to this one. Do you want me to walk you through balancing this one? With, and I use the strategy. Yeah, so all you would do is look at the reference table and you find lithium's atomic number, right? So lithium's atomic number right there. Yeah, so the answer is 3. It's that simple. Okay. So the one I'm looking at right now is June 2022. Okay. So, and somebody asked for balancing. So I'm going to go through this balancing one and then I'll give you a chance to try and answer some of the questions. Okay. So my tip for balancing, okay, is now, do you see how literally oxygen is in everything? Okay, so that's a mess. So what I'm going to do is find the formula that looks the most complicated, okay, and put a 2 in front of it. Okay, so do you remember how I wrote my list of elements before? Okay, so I have Li, I have O, I have H, and I have C. But then remember, if you were with me before, do you remember how I have O in 2 places, right? Okay. So what I'm just making my list of elements first, and then I'll show you. So Li, O, I'm going to put them in the same order, H and C. But now watch, how many Li's do I have? 1. How many O's? In the first spot, 1. How many H's? 1. How many C's? 1. How many O's do I have here? 2. So I have an O here and an O here. Why do I split them? Because if I put a coefficient here, it doesn't change these oxygen, okay? But I have to add them up, so that would be 3 oxygens total, Okay. On this side, subscript for lithium is 2. For carbon is 1. Oxygen, again, is in 2 places. So here it's 3. Here it's 1. So that is a total of 4. And hydrogen is 2. Okay, so I'm going to switch color. That's what I started with. So what I'm going to do is pick the most complicated looking formula and put a 2 in front of it. So you see how this has all these subscripts? I'm going to pick that one. Okay, because right now, is it balanced? No. If it were balanced, I'd be done. Okay, but it's not. So I'm going to put a 2 here and then see if that works everything out. You'd be surprised. Almost all the time it does. So what does that mean? This 2 has to be distributed to everything in the formula. So the lithium times 2, right? The carbon times 2. And this oxygen times 2. So now that's 7. Okay, now let's see if I can make it balance. So on this side, let's fix the lithium times 4, right? So put the 4 here, but I have to distribute it, right? So it's the lithium, which I did, this first oxygen, so now that's 6, and the hydrogen. Okay, so I fixed lithium, perfect. Nothing else is fixed. But how could I fix carbon? Okay, well, it's 2 on this side, 1 on this side. So put a 2 here, right? Times 2. It's 2. And this times 2. 4. So now this is 8. Okay. So now what? Well, I have 4 hydrogens over here, right? I have 2 over here. I know, I hate that they don't give you space for it because it's literally, why would you not want space, right? So I can balance the hydrogens. You see how there's 4 on this side and I have 2 over here? Okay, so times 2 is 4. So the 2 goes here, but remember I have to distribute. So it also affects that oxygen that was 1 of times 2. Oh, and look at that. 6 plus 2 is 8. So that fixed it. It balanced. But, and here's the one glitch that you have to remember, because it will tell you have to balance with the smallest whole number coefficient. So remember how I wrote a 2 in the beginning? Can I divide all of those numbers by 2? I can, right? So I have to. So my complete answer is after I divide them all by 2. So this, what's 2 divided by 2? 1. What's 2 divided by 2? 1. What's 2 divided by 2? 1. And what's 4 divided by 2? 2. That is your answer. Now you can write the ones or you can leave them blank. That's up to you. Okay? But although it seems like, well, why didn't I just start by doing that? You can. I'm just giving you a strategy that almost always works. If you put a 2 in front of the most complicated looking formula, it takes you to, usually takes you to the answer. Yes, I am in Buffalo. No, you don't have to show work at all. You don't have to show work. So my strategy is, my suggestion always, put a 2 in front of the most complicated looking formula and start there. Okay. And you may be like, I I don't know if I can get it to work. Look how complicated this one was. Oxygen was in literally every single thing, and we got to the answer. The worst that can happen is you have to divide everything by 2 at the end. It's not a big deal. Okay. And I know it was January. Was it January 2020? Yeah. Okay. So I'm going to open up that exam. And I know it is a little bit annoying, but I love balancing equations. Yes, you do have to simplify coefficients. So it does have to be in the lowest whole number coefficient. So that's why I did this crossing out and putting the ones at the end. Okay, because if I can divide all of the coefficients by a number, I have to. So do you see how the coefficients were 4, 2, 2, and 2, right? Can I divide them all by 2? I can. 4 divided by 2 is 2. 2 divided by 2 is 1. 2 divided by 2 is 1. And 2 divided by 2 is 1. I will try and do a balancing. I'll see if there's one on this exam too. Let me just go to, it was 66, right? I think. Yeah, this set, right? 60, was it 66? Am I remembering it right? Yeah, you would get it wrong if you didn't divide it, sadly. Yeah, because, and the reason is this. It says, which exam were we looking at? June, that's question 70. Let me show you the wording of the question that explains why. Balance the equation for the reaction using the smallest whole number coefficients. That's why. That's what they put in the wording of the question, so that you have to reduce it if possible. Okay. All right. So looking at this exam, this is January 2020. And we're looking at 66 through 69. Okay. So, all right. First question. First, I'm not even going to read the paragraph unless I need to, because barely ever do I need to. It says compare. What did I tell you about compare? How many answers are there? 3, right? That's it. 3 possible answers. The answers are either they're equal, one is greater, one is less. However you word it, right? Those are the only 3 possible answers. So it says, yep, exactly. That's it. There's only 3 answers. So compare, let's see, let's just look at this exam. And we're going to look for compare. 7 questions. Again, 7 questions where there are only 3 possible answers. Okay. So don't assume that they're all hard, right? Because literally you have a 30% chance. That's better odds than multiple choice. Okay. So compare the chemical reactivities of nitrogen gas and argon gas based on Sir Ramsay's experiment using magnesium. Okay, now I have to read. So I got to look at what it says. Sir William Ramsay is one scientist. Yeah, once in a while there'll be 84 and one of the questions will be 2 points, but basically yes, 85. Is one scientist credited with identifying the noble gas argon. Sir Ramsay separated nitrogen gas from the air and reacted it with an excess of magnesium, producing solid magnesium nitride. However, a small sample of unreactive gas remained with a density different from the density of the nitrogen gas. Sir Ramsay identified the unreactive gas as argon and later went on to discover neon, krypton, and xenon. Okay, this is June 2020. Okay, so to answer your question, this is, no, was it January? January 2020. Oops. Okay, so based on what, here's what I'm going to draw your attention to. Unreactive gas is argon. Okay. The nitrogen from the air reacted it with magnesium. Okay, so compare the chemical reactivities. So first of all, did they both react the same? No, right? So that means one reacted more. So the chemical reactivity of one of them is greater. Which one is it? The chemical reactivity of which one is greater? What do you think? And the answer is in the reading, right? And based on what I highlighted there. Yep, exactly. Perfect. So that's it. Excellent. The reactivity of nitrogen is greater. Nitrogen is greater is also just fine because they literally told you you're just comparing chemical reactivity. So nitrogen reactivity is higher, nitrogen reactivity is greater, nitrogen is greater. All acceptable. Okay. So now let's look at the next one, which is another compare question. We know we only have three answers: greater, less than, equal, right? The density of nitrogen gas to the density of argon gas when both gases are at 298 Kelvin and 101.3 kilopascals. Well, I read that paragraph. It said they were different densities, but did it tell me which was greater or less? So this is a great point to say. You are not expected to remember weird facts and weird numbers. If you're like, well, that's weird that they want me to remember that, it's probably on a reference table. So, what reference table? Right here. So, I'm going to zoom it in a little bit because we need to compare nitrogen right here and argon. What's up, kitty? You hear my cat whining at me? Come on. Come on. She wants to say hi. Okay. And this is the density column. So here's density for nitrogen. And here is density for argon. Now it's decimals. So, okay, come on. Come on. This is Hazel. She's a tortie with a big tortie attitude. But yeah, so when I look, the zeros are the same, the ones are the same. So then I look, the next digit is a 6 and argon is greater, right? So that's that question, right? Now the next one, I think she wants me to let her out of my room. So I'm just going to let her out and, oh, ragdoll, so cute. Here, you want to go out? All right, she was mad because I closed my door earlier. Okay. Yep, you could just say argon is greater. That's perfectly fine. All right, so number 68, state in terms of valence electrons. What does that mean? My answer, better say electrons. Yes, you could say nitrogen is less dense. Absolutely. Yep, you could just say argon is greater. Yep. Absolutely. No, it does not have to be about argon. It could be about either one. So as long as what you say is correct. So argon is greater. Nitrogen is less. The density of nitrogen is less. The density of argon is greater. Argon is more than nitrogen. However you want to word it, as long as you mention one of the gases, don't say it. Like it is a bad word because I don't know what you mean. Mention one of the gases and then say either equal, less, or greater. Okay? So for number 68, your answer must talk about valence electrons. Okay? Why the noble gases that Sir Ramsay discovered have similar chemical properties. So what are the gases he discovered? Let's go back up here. He discovered argon, neon, krypton, and xenon. So let's go to the reference table. We're on the periodic table here. And neon, argon. It definitely just doesn't like highlighting. Oops. Argon, krypton, and xenon. Okay. So, what was my question? In terms of valence electrons. So, looking at the reference table, in terms of valence electrons, why do those gases have similar properties? What do they have in common? Yes. I don't even have to say how many valence electrons they have. I just have to say they have the same. I could say they all have 8 valence electrons. I don't want to say they have the same amount of electrons because they don't. Neon has 10, argon has 18, krypton has 36. So just be careful. The question is worded, it says in terms of valence electrons. Yes, they all have the same last outer shell because that is valence electrons, exactly. So they have 8 valence electrons. They have the same number of valence electrons. Oh, 1 point from passing is just the worst. And then for number 69, state the trend at standard pressure of the boiling points of these noble gases as they are considered in order of increasing atomic number. If you're like, how the heck am I supposed to remember the boiling points? You literally don't have to, right? So what were the noble gases again? Argon, neon, krypton, xenon. So go back to the reference table and look here, boiling point. Okay. Now it says when considered in order of increasing atomic number. So that means I go neon, argon, krypton, xenon. I don't even have to look at all of them. Yeah, so for heat flow, you never say left, right, up, down. I'll go over that in a second. I did that one, but I'll go over it again. So state the trend. So the trend means either it's increasing, it's decreasing, staying the same, kind of similar to a compare question. But usually the trend is going to be increasing or decreasing. Okay. So let's look. I only have to really look at the first two if I'm comparing them. So let's look at neon and argon. Okay. So let's look at neon's boiling point. 27. Argon's boiling point, 87. Let's just do one more, right? Krypton, 120. Yes. So, well, I don't want to say, I want to say the boiling point is increasing because they're all at the same pressure. So I want to say boiling point is increasing. So if I go back to the question, state the trend at standard pressure. It's kind of rude that they put it there because it's just because, why did they put it there? Because this at the bottom of the reference table says the boiling point is at standard pressure. That's why. Okay. So I don't want to say the standard pressure is increasing. I want to say the boiling point is increasing. So everybody, no matter what, people who have like an IEP or a 504 get extra time, maybe sometimes the test read to them, but the score does not change, meaning you still need about 50 points in order to pass, regardless, so that none of that changes. Okay. Okay, so oops. I don't need to move that one over here. Oop. Okay. Move that on the wrong screen. Hold on. What was? Yeah. No, exactly. I'm glad that you are retaining it to pass. That's good. All right. So how do I knew there was a question I wanted to go back to. Remember all the stuff about the elements, like, okay, so if I look at the periodic table, some stuff to remember. Okay, let me just shrink this a little bit. Okay. Hydrogen, we went over this part before. Hydrogen is a non-metal, even though it's over here. And the flow of heat, yes. Okay, so I'm going to answer this question and then go back to the flow of heat. Thank you for that reminder. This side is metals. Okay. Group 1. Here, I'm going to put them up here. The groups that you need to remember. Group 1, alkali metals. Group 2, alkaline earth metals. Groups 3 through 12 are transition metals. Group 17 is halogens. And group 18 is noble gases. Okay. Yeah, they usually do. There's a system in place if people don't pass the exam repeatedly, especially. So if you take the exam at least twice and don't pass, they're more likely to give you kind of a waiver if it's something you need for graduation. Okay. It's okay. Worst case scenario, the balancing equations is going to be one question. So if it's something that you're still struggling with, I would not stress about it too much. Okay. If you know the other stuff for redox, like which way electrons flow in the salt bridge, you'll be fine. So those are the group names to know. You should know the diatomic elements, meaning they're elements that exist as two atoms bonded together. And those are Brinkelhoff, Brinclhof. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Okay, so those are the diatomic elements. And then the liquids on the periodic table, bromine and mercury, one metal, one non-metal. Bromine is the non-metal, mercury is the metal. And the gases are going to sound very familiar to the Brinkelhoff. So it's hydrogen, nitrogen, oxygen, fluorine, chlorine, and then all the noble gases. Those are the gases. Okay. Yeah, I can do that. So I'm going to do heat flow first. So let me see if on this exam, if there is a heat. No, not on this one. Let me see on this one. Nope, not on this one. That's okay. I'll just make a picture. All right. So if I have a beaker of water, okay, doesn't even matter. Okay. And it is at room temperature. Fun fact, you should know room temperature is somewhere between 20 and 25 degrees Celsius. I'll just call it 20. Okay. And this is a common laboratory experiment. I have another beaker and it's above a Bunsen burner. That's my Bunsen burner picture. Okay. And it is boiling. So it is at 100 degrees Celsius. That's a boiling point of water. And inside that water is a block of iron. Doesn't matter. I'll just say iron for this one. Okay. So, and then what I'm going to do is let that boil for a while. Why am I going to do that? Because as I let it sit there in boil in the water at 100, the iron piece is going to be also at 100. So what I'm going to do is then take this piece of iron out of the beaker. It's at 100 degrees Celsius. Why? Because it just came out of the boiling water. I'm going to put it inside this beaker. Okay. Stoichiometry really not important at all. Okay. So I don't even worry about it. So in which way will heat flow? Okay, so I have to look at things that are touching. Okay, the iron block inside here is touching the water, right? So heat will flow from the thing at the higher temperature to the thing at the lower temperature. So I don't say heat rises. I don't say left, right, north, south. I don't say any of that for direction of heat flow. I say from what to what. So in this case, it's going to go from what was warmer to what is colder, always. So from the iron block to the water. So it's got to go from this, because this is at the higher temperature. So it's going to go from this piece of metal to the water. Why? Look at the numbers. See how this is 100 and this is 20. Okay, so from the block to the water. Okay, so from whichever temperature is higher to whatever temperature is lower. If it's just, if I put an ice cube in this water, the ice cube is going to be at 0, right? So, and this water is 20. So what temperature is higher, 0 or 20? 20, right? So it will go from the water to the ice cube. So yes, always from hot to cold. Always from the high temperature to the low temperature. No, always from high temperature to low temperature. So from warm to cold. So we never want to say left, right, north, south, up, down, never. From warm to cold only. Warm to cold. That's it. Always. Warm to cold. Okay, that's it. So high temperature to low temperature. High temperature to low temperature. Okay. Always high to low. Don't say left and right and south. Don't say that. Okay, that's when we get the answers and we're like, oh. No, hot to cold. Not cold to hot. So always, so I'm just going to write it here. Heat flows hot to cold, always. Okay. Hot to cold. High temperature to low temperature. High to low. Okay. All right. High to low. Write an equation. Oh, I was going to do the redox stuff. All right. So let me do redox. Let me see if this one has an electrochem. Oh, here we go. This one has one. And this is still January 2020. So this one, okay, so let's look right here. What kind of cell is this? So there are two kinds of electrochemical cells. There are voltaic and electrolytic. Which one is this one? And how can you tell? So do you know that? Which kind of cell is this and how can you tell? Yeah, excellent. So it is electrolytic and it has a battery. Okay, so that is the evidence. Okay, so battery, same container is partially a clue, but the battery is for sure, right? So it's electrolytic. Okay, so this tells me anode, it tells me cathode. Okay. State the change in oxidation number that occurs. So this one is electrolytic, which I don't necessarily like this. I'm going to do these questions here, but I'm going to find one that's not electrolytic because that's the more common one. Okay. In both of them, electrons go through the wire. Okay. So I'm going to find an example of voltaic as soon as I do this one. Okay. So state the change in oxidation number that occurs for oxygen in the overall reaction. So I need to look here, right? This, remember, single element, 0, single element, 0. This is in a compound, this oxygen. Go to the reference table and you look up oxygen's oxidation state, and it's -2. So in this formula, it's -2. So the oxidation state changes from -2 to 0. Okay. This is a compare question. What are our options for compare? Remember, it can either be greater than, less than, or equal. That is it. You have 33% odds. Okay. The twos, just to answer your question, the twos are up here just to balance the equation. For determining oxidation states, I want to ignore coefficients. Okay. So here, even though there's 2 oxygens, there's no charge up here, so they both have to be 0. This for oxygen, I just got it straight from the periodic table. Oxygen's -2 from right here when it's in a compound. Okay. So compare the number of electrons lost by oxygen to the number of electrons gained by hydrogen. I don't need it for, I don't need hydrogen's number to answer question 83 because I just had to answer how oxygen changed. Okay. Oh, in this one on this side, hydrogen would be, and I see somebody answered it, +1. And the reason is, I'll just put it over here real quick. It's H2O, right? And O is -2, and there's one of them. So my total negative is -2. So my total positive has to be +2. Okay. But I have 2 hydrogens. So each hydrogen would have to be +1. For 83 would be from -2 to 0, because there would be 2 blanks. -2 to 0. That's how oxygen changed. Okay. So compare the number of electrons lost by oxygen to the number of electrons gained by hydrogen. This is a real simple, do you remember this about redox? And the number of electrons lost has to be equal to the number of electrons gained. Okay. All right. So I'm going to, let me see if this exam has, oops. Here we go. This one is better. This is more common, a voltaic cell. So let's look at this one. Okay. What I do is label a bunch of stuff before I ever look at the questions. Okay. So you see how I have magnesium and copper? So I'm going to go to table J first. And I'm going to find both of them on table J. So here's magnesium and here's copper. Which one is higher? Right? So the rule is the higher metal is always negatively charged. So this will have a negative charge. And this will have a positive charge. Now, oops. Since this is voltaic, it tells me it's voltaic. The higher metal is the anode. So that means the lower metal is the cathode. Okay. Then there's this phrase, and which a couple people said earlier, anox and red cat, which means at the anode there is oxidation. Oops. At the cathode there is reduction. Reduction is GR. So that is gains electrons. Remember how we had to write the E negative to show electrons? So this is Leo. So it loses electrons. Why am I saying that? Because, all right, so you tell me as I finish going through that, what do you think questions, anybody have an idea what they think question 78 would be as I finish labeling this, okay? So if it loses electrons, the size of the metal gets smaller. And the side that gains electrons, the size of the metal gets larger. Okay, those are just some facts. I think 78 is purple. Okay, that's for sure not. Okay, so, and how I remember that is I tell my students this, fact, which means the cathode gets fat. It gets bigger as the reaction continues. So a voltaic cell, if you don't know it, is literally a battery. So the cathode keeps getting bigger and bigger. The anode keeps getting smaller and smaller. It's Leo, L-E-O, and GR. So lose electrons oxidation, gain electrons reduction. So the cathode keeps getting bigger and bigger and bigger. The anode keeps getting smaller and smaller and smaller. The battery dies when the anode is no longer. Okay. So Leo stands for lose electrons oxidation, and GR stands for gain electrons reduction. So they say, like Leo says GR, like Leo the lion says GR, like he growls. Okay. All right, and electrons flow. It says fat cat because the cathode gets fat. It gets bigger. That's why I tell my students to help them remember it. So electrons flow through the wire from anode to cathode. So electrons go like this, from anode to cathode. Fat cat, that's it. Well, see, perfect. Now you better remember that one, okay? So electrons flow through the wire from anode to cathode, and through the salt bridge, ions. So that means the positives and the negatives. Like here's an example right here. They flow through the salt bridge in both directions to keep the cell neutral. Okay, that's the purpose of the salt bridge, to allow the ions to flow back and forth and keep the cell neutral. Okay, all right, so I have about 10 more minutes before then I'm going to have to take off. I still have to go to summer school tomorrow and proctor some exams. So 10 more minutes. So I'm going to try to get through as much as I can of this for sure. So 78. I didn't see that. So it says identify the subatomic particles. Well, what did I just say? What flows through the wire? Well, subatomic particles. So it says identify the subatomic particles. So there are 3 subatomic particles. What does subatomic particles mean? There are particles that are smaller than an atom. Yeah, I will scroll right back up real quick. So I'm just going to type these first, and then I will scroll up, okay? So the subatomic particles are protons, 3 things that are smaller than an atom, neutrons, and electrons. So if it says in terms of subatomic particles, those are your only 3 possible answers. All right, there you go. I scrolled up a little bit, okay? So for number 78, it says identify the subatomic particles. So my answer is protons, neutrons, electrons. It could just be one of them, or it could be more than one of them. What is the subatomic particles that flow through the wire? What goes through the wire? Does anybody remember? Yep, you got it. So that's it. It's just electrons. That's the whole answer. Yep, perfect. Just electrons. That's it. They always go from anode to cathode. Ions go through the salt bridge, and that's how they'll get you. So they're going to ask the question, either what moves through the salt bridge or what moves through the wire. So through the wire, it's electrons. Through the salt bridge, it's ions. Okay? And the electrons go from anode to cathode. So since I labeled magnesium as the anode, it goes, and cathode is copper, it's going to go, that's a negative sign on the electron. It goes from anode to cathode. So what is the direction of electron flow? Anode to cathode, always. Okay. Here it literally is the same question from the other exam. Compare greater, less, or equal. 3 answers, right? Compare the number of electrons lost to the number of electrons gained during the reaction on the operating cell. So what is it? No, you can't. It's just going to be just fat cat. Protons don't get involved in this, sadly. So the number of electrons lost and the number of electrons gained, how are they? Are they equal? Is one greater? What do you think? So I just want to say, so when my answer is going to be the number of electrons lost is equal to the number of electrons gained, the number of electrons lost is greater, or the number of electrons lost is less. And the answer is, if magnesium loses 2 electrons, how many electrons are available for copper to gain? So yes, you have 2 electrons, but I don't want to say a number. I just want to say it's the same. Meaning, if magnesium loses 2 electrons, copper gains 2 electrons. So the number of electrons lost is equal to the number of electrons gained. Like when you say 2, you went a step too far. You don't even need to say how many. You just want to say the number of electrons lost has to be equal to the number of electrons gained. Okay? So however many electrons are lost, those are the only electrons available to be gained. Okay? So if I lose 5, I'm going to gain 5. If I lose 5 million, I'm going to gain 5 million. Okay? The number of electrons lost must be equal to the number of electrons gained. Okay? So that is just like the other question. So I'm just going to type it here just to reinforce it. Okay? So the number of electrons lost will always equal the number of electrons gained. Okay. Well, it depends on your school. Ours starts at 8 usually, but it can start. It has to start before 9:15. However your school does it. So some start at 8, some start at 8:30. Okay. So 5 more minutes. This one is good. State the form of energy that is converted to electrical energy in the operating cell. Remember, this was voltaic. So this is chemical to electrical energy. In electrolytic, which was the other one that we looked at, it is the reverse. Electrical to chemical. Okay. 78, I'll type it in here, was electrons. So for subatomic particles, it's one of these or more than one is the answer. So for 78, it is electrons. Yeah, yes. So if it keeps losing electrons, it's a skinny cat. It just doesn't work with anode as well. So fat cat, I usually show a picture of a fat cat that's super cute as a reminder that the cathode gets bigger. Okay. Let's look at this one. It's a relatively easy question. Identify one metal from table J that is more easily oxidized than magnesium. So reference table J. Here's magnesium. What would a metal be that is more easily oxidized? Well, it would be any of these. So those would all be right answers. You just have to say one of them. I'm looking at, which question am I looking at? Number 82. So identify one from June 2022. Identify one metal from table J that is more easily oxidized than magnesium. So here's magnesium. Anything above it is more easily oxidized. Yep. So you could have put any one of those. Remember what we learned from the last one. You can write the symbol or you can write the name of the element, but you cannot write a plus sign when we're using table J. Yes. More active, more easily oxidized. And how do I know? Because oxidizing means losing electrons. And on the periodic table, if I just look real quick, all of the metals have positive oxidation states, which means they lose electrons. So metals are great losers. Metals are the losers. Non-metals are the gainers, but metals are losers. Okay, so yep, you don't have to bring it. I mean, you could bring a pen with you or a pencil. You can't really use a pencil for much on the exam. Everything has to be done in pen, unless it's a graph. But you do get a calculator, and you do go to the room you need to go to. But yeah, you don't. Usually, you do need to bring ID, or your school will have to print out something if you don't have picture ID. Okay, so your school ID with you. But they should give, if you don't have a pen or a pencil, usually they will give you something to use. Okay. Sure, we could name that cat. Yes, we could name the fat cat whatever you want. Okay. If will it help you remember that the cathode gets bigger? Probably not for college. But again, we're going into tomorrow with a positive mindset, right? We're remembering August is usually the easiest exam, right? They're like wrapping up a little present, hopefully giving you were in summer school, you were trying, or you were practicing. You should be rewarded for your efforts, and we're going to have a positive mindset, right? And do well tomorrow. Okay. Remember, pen for everything. Pen on the bubble sheet. Pen, everything's written in pen. The only thing you don't have to write in pen is if there's a graph or like a diagram. Other than that, everything should be in pen. Okay, you don't have to do anything in pencil, but there are very few things that should be done in pencil, unlike math. Yeah, it's because they just to be standard. Sometimes the machines don't pick up pencil that great, so they pick up pen better. So definitely pen on bubble sheets. I mean, it's okay. But the machines are meant to pick up pen better. And like on our bubble sheets, it literally says use black or blue ink on the top of the bubble sheet. So that's the machine likes it better. Okay. And same with like signing it, like you have to sign it in pen. So pretty much I say if you're looking at the bubble sheet, you should be using a pen. Okay. All right, so you can do this. We went through a lot. Remember that the questions in this part of the exam are not necessarily super hard. Don't get discouraged. Use your reference table. Like as soon as it says this, find it on your reference table, right? Okay. Whenever you see something and you're like, I don't know what this is, check your reference table. Okay. There are a lot of kind of hints and helps along the way in your reference table. Okay. So I believe in you. You can do it. Don't forget to come back, share what you ended up getting on the exam. We should all dream about fat cats tonight. 74. What was that? Oh, it is heat, but heat as a product. Heat on the product side. Heat is coming out. Heat on the right side. Something like that. Okay. No, they don't. Not unless there's a 2-point question, and those are pretty rare. I can't even remember the last time there was a 2-point question. We should all be dreaming about fat cats, honestly. Those would be great dreams. So if it's a fat cat teaching you about some chemistry, that's even better. So I would say for 74, what I would say is heat is a product, okay, or heat is on the right side, or heat is coming out of the reaction. Something like that. Okay. Why can't you just say products? Because the evidence that it's exothermic, you have to say heat, because that's the evidence that it's exothermic. Yeah, heat is on the right side. Heat is a product. Heat is coming out of the reaction. Heat is lost. That's okay. But the evidence for exothermic has to involve heat or energy. So if you just say products, that doesn't tell me that you knew what on the product side showed exothermic. Okay, so you had to say the heat, and then you had to say which side it was on. Okay. Yeah, it depends. You'll get your results. It depends on how quickly your school gets them graded within a week. There are a lot, yes, who are retaking the chemistry regents. So this is definitely a lot. So we'll see how it goes. I'm hoping for the best. I have confidence in you. You were here reviewing, so that already says a lot about you. All right, I could do 75, last one. Let's see. Explain in terms of substances why the reaction is a decomposition reaction. Remember what I said before? I could do 75, 76, and then I'm going to have to stop. Okay. So decomposition, remember, means breakdown. So it means where you start with something connected, and then on the other side, it's broken apart. Okay. So explain in terms of substances why the reaction is a decomposition reaction. You could just simply say 1 reactant and 2 products. Okay. 1 substance breaks apart. There are more products than reactants. Something along those lines. Okay. You could say the reactant breaks apart. Yes. This is June 2022. Yes. You could just say the reactant breaks apart or breaks down. That's also okay. So the reactant breaks apart or the reactant breaks down. So 70, all right, I guess I'll do 76 and 77, and then really I have to go, okay? So state how increasing the temperature of the H2O2, that's hydrogen peroxide, affects the rate of the reaction, okay? So rate of reaction, when we increase temperature, rate increases. You could also increase rate by adding a catalyst, by increasing concentration, by increasing surface area, okay? And then 77, heat of reaction is the difference between products and reactants. So it's this. They wanted you to draw a double arrow like that. No, that's okay. So I did some, now you want 78. Let me see if 78 is, I did 78 already. And 79. Yes. So higher temperature, higher rate, right? So I just moved it down here because I already did 70, 78, 79, and 80. So higher temperature, higher rate. So if I go back to this one, okay, so how to increase rate, increase temperature, add a catalyst, increase surface area, which means break in smaller pieces. Okay, those are ways to increase rate. Okay. Come on now. You have to be nice. I stayed way extra. So you have to be nice to each other. Okay. So, that is it. That was even 8 minutes longer than I said I was going to stay. Good luck to everyone tomorrow. And do your best. Go in positive mindset, confidence, and you can do this. Okay. Dream of fat cats. Okay. You're welcome, everyone. Good night. Good night. And do awesome tomorrow. Okay.